Let us continue with the transverse and longitudinal waves. So if the particles of the medium vibrate in the same direction as the propagation of a wave, such waves are called as longitudinal waves. These longitudinal waves, they are characterized by alternate compressions and wave fractions. These compressions, they are the regions of higher density. So compressions are the regions of higher density. Wave fractions, they are the regions of lower density. So longitudinal waves, they can be generated or they can be set up in solids, liquids and gases. So these longitudinal waves cannot be polarized. So these are the few characteristics of longitudinal waves. So if the particles of the medium vibrate in the same direction as that of the propagation of wave, such waves they are called as longitudinal waves. So best example for longitudinal waves is sound waves. And these longitudinal waves, they are characterized by alternate compressions and wave fractions. Compressions, they are the regions of higher density, and wave fractions, they are the regions of lower density. And these longitudinal waves, they can be generated or they can be set up in solids, liquids and gases. Longitudinal waves cannot be polarized. Transverse waves. So if the particles of the medium vibrate at right angles to the direction of propagation of the wave, such waves they are called as transverse waves. Waves on the surface of water, so they are transverse waves. Light waves, X-rays, UV rays, so all these they are the examples for transverse waves. Transverse waves, they are characterized by alternate crest and troughs. In a transverse wave, a particle is said to be in crest if it has a maximum displacement along a positive direction. And in a transverse wave, a particle is said to be in trough if it has a maximum displacement along a negative direction. Transverse waves, they can be generated only in solids and liquids. These solid transverse waves can be polarized. So longitudinal waves, they cannot be polarized, but transverse waves can be polarized. And they can be generated only in solids and liquids, and they are characterized by alternate crest and troughs. A particle is said to be in crest if its displacement is a maximum along positive direction, and a particle is said to be in trough if it has a maximum displacement along negative direction. So those are the differences between longitudinal waves and transverse waves. Pulse, a single wave is called pulse or the wave pulse. A single wave, it is called as pulse. If the calm surface of water is pricked with a sharp needle, a wave pulse is generated. A continuous wave, it consists of a series of wave pulses which are generated one after the other. So a single wave, it is called as the pulse or wave pulse, and a continuous wave, it consists of a series of wave pulses which are generated so one after the other. So let us define some of the terms which are related to waves. Wave amplitude, wave period, wave frequency, wave velocity, wavelength. So these are the few terms which are associated with waves, either it may be a longitudinal wave or a transverse wave. The maximum displacement of the particles of the medium from the mean or equilibrium position, it is called as wave amplitude. Maximum displacement of particles of the medium from mean or equilibrium position, it is called as wave amplitude. So generally wave amplitude, it will be measured in meter. Wave period, the time taken to set up one complete wave in a medium, it is called wave period. It is also defined as the time taken by the oscillating particle. Time taken by the oscillating particle to complete one oscillation. So it is the time taken to set up a single wave in a medium, or it is the time taken by the oscillating particle to complete one oscillation. So it is expressed in second. Wave frequency. The number of waves set up in a medium in 1 second. Number of waves set up in a medium in 1 second. It is called wave frequency. Or the number of oscillations completed by oscillating particle in 1 second. It is called as wave frequency. T is equal to 1 by f, or f is equal to 1 by t. So it is expressed in per second or hertz. The distance traveled by a wave. Distance traveled by a wave in 1 second is called wave velocity. So the distance traveled by a wave in 1 second, it is called wave velocity. So it is measured in meter per second. Wavelength. So this is a transverse wave. So this is amplitude. Crest. Stop. So it is defined as the distance between two consecutive crests or two consecutive troughs in a transverse wave. The distance between two consecutive crests or troughs in a transverse wave, so it is called as wavelength. Compression. Rarefaction. The distance between the midpoints of the consecutive compressions or the consecutive rarefactions in a longitudinal wave is also defined as wavelength. The distance between two points or particles in a medium which are in same state of vibration is called wavelength. The distance between two points or particles in a medium which are in same phase or which are in a same state of vibration, it is called as wavelength. It can also be defined in another way. The distance traveled by a wave in a time interval equal to its time period is called wavelength. So in case of transverse wave, wavelength is defined as the distance between two consecutive crests or troughs. In a longitudinal wave, the distance between the midpoints of two consecutive compressions or rarefactions, it is defined as wavelength. Or the distance between 2 points of particles in a medium which are in same state of vibration or which are in same phase, it is also called as wavelength. Or it can also be defined as the distance traveled by a wave in a time interval equal to its time period. It is called as wavelength. And wavelength is measured in a meter. So these are the important terms which are associated with waves. And we have another term, phase. Phase of a vibrating particle at any instant indicates the state of vibration of the particle at that instant. So phase of a vibrating particle at any instant, it indicates the state of vibration of particle at that instant. Now in this diagram, now let us consider P and Q. So now these two particles, they are in the same phase or same state of vibration now. The distance between these two particles or these 2 points which are in the same phase or same state of vibration, it can also be called as wavelength lambda. And the phase of vibrating particle at any instant, it indicates the state of vibration of the particle at that instant. See, in case of a simple harmonic wave or a particle which executes a simple harmonic motion in a time interval equal to its time period, it describes an angle 2 pi. In a time interval equal to its time period, it describes a total angle of 2 pi. Therefore, the phase of vibrating particle at t by 4, it is pi by 2. At t by 2, it is pi. At 3t by 4, it is 3 pi by 2. And at t, it is 2 pi. Phase of a vibrating particle, it is a fraction of the time period that has elapsed since the particle last passed through its mean position in positive direction. So therefore, now if you consider this reference point, this is a reference point. So at this point, in terms of time period, it is t by 4, and in terms of angle it is pi by 2. That represents the phase, that is t by 4 and pi by 2. At t by 2 it is pi, at 3t by 4 it is 3 pi by 2, and at t it is 2 pi. So therefore, as the wave propagates through a material medium, different particles are disturbed at a different instant of time. In the sense, different particles are in a different state of vibration. So if two particles are in different states of vibration, then there exists phase difference between those two particles. So as the wave propagates through a material medium, different particles of the medium, they are disturbed at different instants of time. If two particles are in a different states of vibration or in different phase, then there exists a phase difference between those two particles. From this diagram, so we can have a conclusion that a path difference of lambda corresponds to a phase difference of 2 pi. So a path difference of lambda, it corresponds to a phase difference of 2 pi. So if two particles are in different states of vibration, they are in different phase. As a result, there exists a phase difference between those two particles, and a path difference of lambda corresponds to a phase difference of 2 pi. So it's a very important concept. So generally, while solving the numericals, if you want to convert path difference to phase difference or phase difference to path difference, you can make use of these relations. Path difference is equal to lambda by 2 pi into phase difference. You can convert the given phase difference into path difference using this equation. Phase difference is equal to 2 pi by lambda into path difference. So these two equations, they can be used to convert the given phase difference to path difference or given path difference to phase difference. First, you should be familiar with this concept. A path difference of lambda, it corresponds to a phase difference of 2 pi. So therefore, path difference is equal to lambda by 2 pi into phase difference, or phase difference is equal to 2 pi by lambda into path difference. From the diagram, it is clearly indicated, or you can clearly understand that a path difference of lambda corresponds to a phase difference of 2 pi. So therefore, path difference is written as lambda by 2 pi into phase difference, or phase difference it is given as 2 pi by lambda into path difference. So these two are used for converting phase difference to path difference or path difference to phase difference. Relation between wave velocity frequency and wavelength. Let us consider a wave which is traveling in a medium with a definite velocity v. So it is traveling in a medium with a definite velocity v. Let t be its time period and lambda be its wavelength. V represents V represents the distance traveled by a wave in a time interval equal to its time period. So V is nothing but the wave velocity. It represents the distance traveled by a wave in a time interval equal to its time period. Wave velocity is equal to distance traveled by time period. So already we are familiar that the distance traveled by a wave in a time interval equal to its time period. It is nothing but called as wavelength. So therefore, wave velocity V is equal to, so distance traveled by a wave in a time interval equal to its time period, it is nothing but wavelength lambda by time period T. V is equal to f lambda, because 1 over T is nothing but frequency. So now this equation gives the relation between wave velocity, frequency and wavelength. This is for a wave. So in the last class we have seen the particle velocity and particle acceleration executing simple harmonic motion. Particle velocity, it is given by V is equal to omega into root of a square minus y square. So this equation, it represents the velocity of a particle executing simple harmonic motion. That is V is equal to omega into square root of a square minus y square. This is called particle velocity, and this is called as wave velocity, which is given by V is equal to f lambda. So generally we will be using this equation for solving wave velocity, and this is for solving particle velocity. As the wave propagates through a material medium, it transfers energy from one point to another point. The average rate at which energy is transmitted, in the direction of propagation of wave, it is called as power transmitted by a wave. The average rate at which energy is transmitted in the direction of propagation of wave, it is called as power transmitted by a wave. Power transmitted across unit area. Power transmitted across unit area perpendicular to the direction of wave propagation is called intensity of a wave. Power transmitted across unit area perpendicular to the direction of wave propagation is called intensity of a wave. So intensity generally is written as power transmitted across unit area. The unit is watt per meter square. The expression for intensity of a wave. So it is a fluid relation. Intensity of a wave, it is given by the equation I is equal to 2 pi square f square a square rho into v. So intensity of a wave, that is the expression for intensity of a wave. So it is 2 pi square f square a square rho into v, where f it is wave frequency, a it is wave amplitude, v wave velocity, and rho it is the density of the medium. Through which wave propagates. So rho is the density of the medium through which the wave propagates. See, for a given wave, f and v are constant, and for a given medium, density remains constant. Intensity varies directly with the square of the amplitude. So for a given wave, f and v are constant, and for a given material medium, density is constant. Therefore, intensity of a wave it is proportional to square of the amplitude. So progressive wave, or it is also called as traveling wave. A wave which moves continuously in a medium in the same direction without change in its amplitude. Without change in its amplitude is called a progressive wave or traveling wave. A wave which moves continuously in a medium in the same direction without change in its amplitude. Such a wave it is called as progressive wave or traveling wave. So equation of progressive wave. So if the wave moves continuously in a medium in the same direction without change in its amplitude, such a wave it is called as progressive wave or traveling wave. So it can be shown that the equation for a progressive wave which is traveling along a positive x-axis, it is given by y is equal to a sin omega into t minus x by v. So this equation it represents the equation of a progressive wave, and the wave which travels along positive x-axis. If the wave is traveling along the negative x-axis, so then it is represented by y is equal to a sin omega into t plus x by v. So these two equations they represent the equations of progressive wave. This equation it is traveling along the positive x-axis, and this equation it is traveling along the negative x-axis. Using this equation, so you can obtain the different forms of the equations of progressive wave. Y is equal to a sin omega is written as 2 pi f into t minus x by v. Y is equal to a sin 2 pi f into t minus f into x by v, y is equal to a sine 2 pi t by capital T minus x by lambda. So here f by v, it is taken as 1 over lambda. So we have this relation v is equal to f lambda 1 by lambda is equal to f by v. So therefore this f by v, so it is written as x by lambda. Y is equal to a sine 2 pi into t by t minus 2 pi x by lambda. Y is equal to a sine omega t minus kx. So here omega is 2 pi by capital T. So k is equal to 2 pi by lambda. So this k is called as wave number or propagation constant. So it is wave number or propagation constant. So generally, so in numericals we will be given an equation which represents a progressive wave. Sometimes it may be in standard form or sometimes it may not be in standard form. So before solving the equation of a progressive wave, to find either the frequency, time period, wavelength or wave velocity, so first you should reduce the given equation to any one form of the standard equations. Then only you should proceed to solve the other unknowns which are asked in your numericals. So you can make use this equation a sine 2 pi into f into t minus fx by v. So t by capital T minus x by lambda. So and this 2 pi by t, it is taken as omega, and 2 pi by lambda, it is taken as k, that is wave number or propagation constant. So these are the different forms or the equations which represent progressive wave. So this equation y is equal to a sine omega into t minus x by v already we have derived in our theoretical sessions. Speed of transverse wave in a string. So the physical quantities which determine the speed of a transverse wave in a string are tension in the string, and second one is mass per unit length. So this is called linear mass density. So the two physical quantities which determine the speed of a transverse wave in a string, one is the tension in the string, and the second physical quantity is mass per unit length, or it is called as linear mass density. V is equal to square root of T by mu, where T tension in the string, mu, so this is the linear mass density. So if you want to just verify how this equation represents the speed of transverse wave, we just move to the dimensional formulas. V is equal to, let us consider this as square root of T by mu. square root of tension is nothing but force. M power 1, L power 1, T power minus 2. Mass per unit length. M power 1, L power minus 1. So this represents linear mass density. This represents the tension, the dimension formula for tension and linear mass density. Square root of L power minus 1, if you take up the numerator, you get L power 2, T power minus 2. So if you take the root, this is nothing but velocity now. L power 1, T power minus 1. So therefore this equation, it represents the speed of transverse wave in a string. So that is T is tension in the string and mu is linear mass density. So we know that the density is equal to mass by volume. Density is equal to mass by area into length. Volume is known as area into length. So now this mass per unit length, it is nothing but called as a linear mass density. So therefore rho is equal to mu by A, or mu is equal to rho into A. So therefore velocity, so it is expressed in terms of density of material of the string. So it is given by the equation T divided by rho into A, where T is the tension in the string and rho is the density of the material of the string. So this is the expression for speed of transverse wave in terms of tension and density of material of the string. This is in terms of tension in the string and mass per unit length. That is the speed of transverse wave in a string. Speed of longitudinal wave. Speed of longitudinal wave is given by V is equal to square root of E by rho, where E modulus of elasticity of the medium, rho is the density of the medium. In case of solids, M is nothing but that is the modulus of elasticity is nothing but the Young's modulus Y. So therefore we get V is equal to root of Y by rho. That is in solids, modulus of elasticity, it is just replaced or it is substituted by Young's modulus. In case of liquids, E is, that is the modulus of elasticity, it is replaced by bulk modulus. So therefore we get V is equal to square root of B by rho. So here Y is Young's modulus and B is the bulk modulus. So we have already studied that Young's modulus is quite larger when compared to bulk modulus. So therefore speed of sound in solids is much greater when compared to speed of sound in liquids and gases, since Young's modulus is greater than bulk modulus. So Young's modulus is quite larger when compared to bulk modulus, hence the speed of sound So it is more in solids when compared to liquids and gases. Sound is nothing but a longitudinal wave. So therefore, speed of sound it will be more in solids when compared to liquids and gases. So velocity of sound in a gas. So Newton's formula. See, Newton has given an expression for the speed of sound in any medium, which is given by V is equal to square root of E by rho. So as we have considered in the previous case, E is the modulus of velocity of the medium and rho is the density of the medium. For an ideal gas, the pressure P, volume V and temperature T, so they are related by PV is equal to NOT, where N is the number of moles of the gas and R is the universal gas constant. According to Newton, the propagation of sound in gaseous medium, it takes place at constant temperature. That is, it is an isothermal process. So Newton argued that the propagation of sound in a gaseous medium, it is an isothermal process. That is, it takes place at constant temperature. So for isothermal process, so we can consider PV is equal to constant, because isothermal process means it is nothing but temperature remains constant. So now you differentiate this equation with respect to V on both the sides. P plus V into dP by dV is equal to 0. Just I have differentiated both the sides. P into dV plus V into dV is equal to 0. P into dV is equal to, so P into dV is equal to minus V into dP. P is equal to minus V into dP by dV. P is equal to minus dP so now this dV by V, it represents the strain. dP, it represents the stress. So generally in gaseous medium, we will consider the bulk modulus. So therefore, B is equal to, P is equal to minus dP by dV by V. So this is nothing but stress now. In terms of pressure, that is the force per area. This is nothing but strain. So this P is now, it is replaced by bulk modulus. Now if you just substitute this condition in Newton's formula, that is if E is equal to B and that is equal to P, where E is the modulus of velocity So here it is nothing but the bulk modulus. Now it is replaced by P. So here V is equal to square root of P by rho. So this formula, it is called as the Newton's formula for speed of sound in gas. At NTP, at normal temperature pressure of air, it is 1.013 into 10 power 5 Pascal. And at NTP, density of air, it is 1.293 kg per meter cube. Upon substituting these two values in the Newton's formula, that is V is equal to square root of 1.013 into 10 power 5 by 1.293. So it comes out to be 280 meter per second. This is not in good agreement with the speed of sound in gas, which is experimentally determined. It is around 332 meter per second. So nearly there is a 16% error. So therefore, Newton's formula requires a correction, and that correction it was given by Laplace. So now let us move to Laplace correction. See, according to Newton, sound propagates in a gaseous medium is an isothermal process, in the sense the temperature remains constant. But if you consider that as an isothermal process, and if you just find the speed of sound in gas, it comes out to be 280 meter per second. There is an error around 16% because the speed of sound in gas is around 332 meter per second. So therefore, Laplace argued that the propagation of sound in a gas, it is not an isothermal process, rather it is an adiabatic process. As the sound propagates in gaseous medium, in the regions of compressions, there is a slight increase in temperature, and in the regions of rarefactions, there is a decrease in temperature. And this process, it occurs so quickly or rapidly that there is no time for equalization of heat or temperature. And moreover, air is an insulator. It's a bad conductor of heat. So therefore, the propagation of sound in a gas, it doesn't take place at the constant temperature. In the sense, it is not an isothermal process, rather it is an adiabatic process. In the sense, the temperature does not remain constant, and there is no time for equalization of temperature or heat. So in compressions and rarefactions, as a result, it is not an isothermal process, rather it is an adiabatic process. Therefore, Laplace has given a correction. So now, modulus of elasticity, so it will be taken as gamma p. So here gamma, it is a ratio of specific heat capacities at constant pressure and constant volume. So therefore, we will get back the relation for speed of sound in gas as V is equal to square root of gamma p by rho. So for air, gamma, so it is 1.4. So now if you just substitute the same values in this equation now, so the speed of sound in gaseous medium, it comes out to be 331.2 meter per second. So it is in good agreement with 332 meter per second. And this formula, it is called as Newton's Laplace formula. V is equal to gamma p by rho. So where gamma is the ratio of specific heat capacities at constant pressure and constant volume. Gamma is taken as Cp by Cv, and Fourier gamma is taken as 1.4. Upon substituting the values in this Newton's Laplace formula, the speed of sound in gas, it comes out to be 331.2 meter per second, and this value is in good agreement with 332 meter per second. Factors affecting speed of sound in gas of parastatic pressure. So we know the expression for speed of sound in gaseous medium, which is given by V is equal to gamma P by rho. So when you just analyze this relation, so you can observe that speed of sound, so it depends upon pressure. From Boyle's law, at constant temperature T, the pressure of a given gas, it varies inversely with volume. Provided temperature constant, pressure is inversely proportional to volume, or PV is equal to constant. Density is equal to mass by volume, where M is the mass and V is the volume. For a given mass, so now volume can be written as M by rho P into M by rho. For a given mass at constant temperature, as pressure increases, proportionately density also increases. So for a given mass M, as P increases, as pressure increases, density also increases. Therefore, the ratio P by rho, it remains constant. That is, for a given mass, when temperature is constant, when P increases proportionately, density also increases. Thereby, this ratio P by rho, it remains constant. So, if this ratio P by rho remains constant, then speed of sound in a gas, speed of sound in a gas is independent of pressure at constant temperature. So provided at constant temperature, so speed of sound in a gas, it is independent of pressure, because for a given mass, as pressure increases, density also increases, because we have considered temperature as constant. And if pressure and density increase proportionately, the ratio P by rho, it remains constant. Therefore, speed of sound in a gas, it is independent of pressure, or it doesn't depend on pressure at constant temperature. Let us consider the effect of temperature. From Charles' law, at constant pressure, the volume of given mass of gas is proportional to temperature. V is directly proportional to temperature. So at constant pressure, the volume of given mass of gas is proportional to temperature. As temperature increases, volume also increases. When volume increases, automatically density decreases. Therefore, density is inversely proportional to temperature. So when volume increases, that is when temperature increases, volume also increases. But when volume increases, density automatically decreases. Therefore, density is inversely proportional to temperature. So therefore, V is equal to square root of 1 by 1 over T, because we have considered pressure as a constant and gamma it is a ratio of specific heat capacities. So therefore, V is equal to root of 1 over 1 over T, or V is directly proportional to T. That is the speed of sound in a gas. It is directly proportional to square root of absolute temperature. So V is directly proportional to square root of T, or it is directly proportional to square root of absolute temperature. But when you consider pressure, speed of sound in a gas is independent of pressure provided at constant temperature. Now let us study the effect of temperature. From Charles' law, at constant pressure, the volume of given mass of gas it is directly proportional to temperature, or V is proportional to T. As temperature increases, volume increases. But when volume increases, automatically density decreases. Therefore, density and temperature are inversely proportional. So you get V is equal to root of 1 over T, or V is proportional to square root of T. That is speed of sound in a gas. It is proportional to square root of absolute temperature. Stationary waves. Or they are also called as standing waves. Stationary waves are produced due to superposition of two identical waves having same frequency and amplitude, traveling with the same velocity but in opposite direction. So stationary waves are produced or generated due to superposition of two identical waves. So identical in the sense they should have the same frequency and amplitude, traveling with same speed but in opposite direction. Now let us consider two harmonic waves. They are traveling in opposite direction with the same speed v, with the same amplitude a. Let me represent one harmonic wave a sine omega t minus kx. So this is moving along the positive x-axis, a sine omega t plus kx. This is moving along the negative x-axis. So they are having the same speed, same amplitude, frequency and wavelength, but they are traveling in opposite direction. When they superpose, then there is a formation of stationary waves. These stationary waves, they are called as standing waves because there is no flow of energy across any section of the medium once there is a formation of stationary waves. Hence, they are also called as standing waves. When stationary waves are generated or standing waves are generated, at certain points in a medium, the particles of the medium are permanently at rest. Such points they are called as nodes. So when stationary waves are generated or produced, at certain points in a medium, particles of the medium are permanently at rest. They are called as nodes. And at some points, the particles of the medium have maximum amplitude of vibration. Those points they are called as antinodes. In stationary waves, nodes and antinodes they are equally spaced. A node is generated between two successive antinodes, or an antinode is generated between two successive nodes. The distance between two consecutive antinodes or two consecutive nodes, it is lambda by 2. Distance between two consecutive nodes or antinodes, it is lambda by 2. And the distance between a node and an antinode, it is lambda by 4. And at nodes, the particles of the medium are permanently at rest. At antinodes, the particles of the medium have maximum amplitude of vibration. And the region or the space between two nodes, it is called as loop or segment. And the particles within the loop or segment, they vibrate in phase. Now if you consider these two for the harmonic waves which are traveling in opposite direction, and when they superpose, there is generation of stationary waves. From the principle of superposition, then you can consider y is equal to y1 plus y2. That is y is equal to a sine omega t minus kx plus sine of omega t plus kx. So just I have taken a as common here. So this is in the form of sine a minus b plus sine a plus b. So by using the trigonometric identity, so now I can consider this equation y is equal to 2a sine omega t cos kx. Y is equal to r sine omega t, where r is equal to 2a cos kx. So where that r represents the amplitude of the resultant wave or the stationary wave. That is, r is equal to 2a cos kx. Here r represents the amplitude of the resultant wave, that is stationary wave, which is generated due to superposition of these two identical waves which are traveling with same speed but in opposite direction. Here r represents the amplitude of the resultant wave or the stationary wave. if cos kx is equal to n pi, then the resultant amplitude r is equal to plus or minus 2e. X. See, from this equation, we are familiar that as the position varies, amplitude also varies. Here x is the position. As the position varies, amplitude or resultant amplitude also varies. If cos kx is equal to n into pi, then amplitude is r is equal to plus or minus 2a. X is equal to so n into pi by so if you consider that relation, so you get r is equal to 2a n into pi. If you just go on giving the values for n, if n is 0, so this becomes cos 0. So therefore you get 1, then you get plus 2a. So we just go on varying the values of that cos kx. So then you will get the values as so plus or minus 2a. Now if this condition is satisfied, so then you will get maximum amplitude. Here there is generation of antinodes. And if cos, just a small rectification here. If kx is equal to n into pi, so just I will consider this kx. If kx is equal to n into pi, so then you get r is equal to plus or minus 2e. X is equal to n into pi by k. X is equal to n into pi by k can be written as 2 pi by lambda. X is equal to n into lambda by 2. So now n takes the value 0, 1, 2, 3 and so on. X is equal to lambda by 2. X is 0, lambda by 2. Next we get lambda, 3 lambda by 2. Next we get 2 lambda and so on. So here amplitude will be maximum, and at these points we get antinodes. If kx is equal to 2n plus 1 into pi by 2, so then amplitude is 0. X is equal to 2n plus 1 into pi by 2k. This is equal to 2n plus 1 into pi into, so k is written as 2 pi by lambda. X is equal to pi and pi, we get 2n plus 1 into lambda by 4. So now if you just substitute the values n is equal to 0, 1, 2, 3 and so on, you get x is equal to, if n is taken as 0, you get lambda by 4. If n is taken as 1, you get 3 lambda by 4, if n is taken as 2, we get 5 lambda by 4. At these points, there is a generation of nodes. At x is equal to 0, lambda by 2, lambda, 3 lambda by 2, 2 lambda, there is generation of antinodes. And at x is equal to lambda by 4, 3 lambda by 4, 5 lambda by 4, and so on, there is generation of nodes. And in the previous diagram, we had seen that the distance between two nodes or antinodes, it is lambda by 2. Distance between node and antinode, it is lambda by 4. Now let us consider at x is equal to 0, there is generation of antinode. At x is equal to lambda by 2, there is generation of antinode, lambda, antinode. Now the distance between two nodes or two antinodes, it is lambda by 2. Now we just consider the difference between these two. X is equal to 0 and lambda by 2. You will get lambda by 2. That is distance between two antinodes. Or you take the difference between lambda and lambda by 2. You get once again lambda by 2. That is the distance between two consecutive antinodes. 3 lambda by 2 minus lambda. You will get lambda by 2. 2 lambda minus 3 lambda by 2. Once again you will get lambda by 2. So now let us move to this relation now. Distance between two consecutive nodes, it is also lambda by 2 itself. 3 lambda by 4 minus lambda by 4 is equal to 2 lambda by 4. This is equal to lambda by 2. The distance between two consecutive nodes, once again it comes out to be lambda by 2. Or the distance between two consecutive antinodes, it is also lambda by 2. Okay, now let us see what is the distance between this node and antinode. At x is equal to 0, we are having a antinode. At x is equal to lambda by 4, we are having a node. Now when you just consider the distance between antinode and node or node and antinode, it will be lambda by 4 minus 0. It is equal to lambda by 4. This is distance between two nodes. Distance between node and antinode. Lambda by 4 minus 0. It is lambda by 4. And once again at lambda by 2 you are having an antinode. At 3 lambda by 4 you are having a node. So once again when you take the difference you get the distance between node and antinode as lambda by 4. So therefore in stationary waves, nodes and antinodes are equally spaced. The distance between two consecutive nodes or antinodes, it is lambda by 2, and the distance between node and antinode is lambda by 4. And this equation, so that is y is equal to 2a sine omega t cos kx. It represents a stationary wave or standing wave, or y is equal to r sine omega t. So where r is the amplitude of the stationary wave, it is given by 2a cos kx. Now by considering the same equation, I have considered the condition here. If kx is equal to n into pi, so then r will be plus or minus 2a. So then you can find out at what positions antinodes are generated. At x is equal to 0, lambda by 2, lambda, 3 lambda by 2, 2 lambda, there is a generation of antinodes. And if kx is equal to 2n plus 1 into pi by 2, so then amplitude will be 0. That is the points where the nodes are generated. So then it is lambda by 4, 3 lambda by 4, 5 lambda by 4. And from these calculations, we can find that the distance between two nodes or antinodes is lambda by 2, and the distance between node and antinode is lambda by 4. So this is one of the important topics, air column. So now if you consider a pipe which is open at both the ends, or let us consider a pipe which is open at one end and closed at the other end. This is called open pipe. This is called closed pipe. And along the length of the pipe, so you are having a column of air. So in this length, you are having a column of air. A column of air enclosed within a pipe, either it may be an open pipe or closed pipe. It is called as air column. Generally, you are having two types of pipes. One is open pipe and the second one is closed pipe. If the pipe is open at both the ends, it is called open pipe. And if the pipe is open at one end and closed at the other end, it is called as closed pipe. Either it is open pipe or closed pipe, along its length it encloses a column of air, it is called as air column. When sound is produced in open air, the air particles have maximum freedom of movement. That is, when sound is produced in open air, the air particles, they have maximum freedom of movement. But when the same sound is produced, or when air is blown across the mouth of an open pipe or closed pipe, the air column or the air particles, they have restricted movements. But when sound is produced in open air, the air particles have maximum freedom of movement. But when air is blown across the mouth of an open pipe or closed pipe, generally there is also generation of sound, but the air particles, they will be having restricted movements. So now this is the open end, this is another open end, this is also open end, this is also open end. Now when you blow the air at the mouth of either open pipe or closed pipe, there is a generation of longitudinal waves. And these longitudinal waves, they will travel to this fixed end, and there is a reflection. So due to superposition of both the incident and reflected waves, there is generation of stationary waves in the open pipe or closed pipe. Now let us see the mode of vibration of air column in closed pipe, then we will move to open pipe. So before going to mode of vibration of air column in closed and open pipe, so let us see few terms which are associated with the vibrations of air column. When air is blown at the mouth of the open end of the pipe, the air column vibrates in different modes. The air column vibrates in different modes. First, let us blow the air with a smaller force or smaller pressure. Air column vibrates. That is one mode of vibration. If you just blow the air with the greater speed, once again the air column vibrates, but the mode of vibration will be different. The lowest possible mode of vibration of air column with the lowest possible frequency, it is called as fundamental mode of vibration. It is called as fundamental mode of vibration, and the corresponding frequency, it is called as a fundamental frequency. The lowest possible mode of vibration of air column with the lowest possible frequency, it is called fundamental mode of vibration, and the corresponding frequency, it is called as a fundamental frequency. And the next higher modes of vibration with frequencies greater than fundamental frequency, they are called as overtones. In the sense, the frequency is greater than fundamental frequency, they are called as overtones. And the overtones, which are the integral multiples of fundamental frequency, they are called as harmonics. So one thing what we should note here is, so generally, so when air is blown across the mouth of the pipe, there is generation of stationary waves due to superposition of the incident and reflected waves. And when air is blown, the air column starts to vibrate. Air column vibrates in different modes. The lowest possible mode of vibration of air column with the lowest possible frequency, it is called fundamental mode of vibration, and the corresponding frequency, it is called as fundamental frequency. And the next higher modes of vibration with the higher frequencies, in the sense frequency greater than fundamental frequency, they are called as overtones. And the overtones, which are the integral multiples of fundamental frequency, they are called as harmonics. So the overtones, which are expressed as integral multiples of fundamental frequency, they are called as harmonics. Generally, overtones will be having frequency other than fundamental frequency or greater than fundamental frequency, and those are called as overtones. And the overtones, which are expressed as integral multiples of fundamental frequency, they are called as harmonics. So next we are supposed to study the mode of vibrations of air column in closed pipe and open pipe. So generally in numericals, the problems related to mode of vibration of air column in closed pipe and open pipe will be frequently asked. So that's where we discuss those concepts and Doppler effect in the next session. Talking about